For our Thursday colloquium, and I'm very glad that people have been with us as we were discussing right from the beginning of April, and we find quite a lot of the same people listening to the colloquium from all over the world. And the heartening thing is that every time we find new people joining us, which is wonderful. And we've tried to keep our menu here quite varied, like we do in our in-person colloquium at IUCAA, which I suppose is not going to resume for a while now. But we find this medium over Zoom so far-reaching that I think we're tempted that we'll keep a form of this going for a long time now. It's a pleasure for us to welcome Bhal Chandra Joshi from TIFR NCRA right across the road to give a talk on pulsar timing arrays. It's one. I just was wondering. Bhal Chandra Joshi has been with us for so long, and he's been a part of our joint IUCAA NCRA teaching and research work forever, it seems, but it actually seems that he had a life before that. He did his undergraduate from IIT Roorkee, then postgraduate from IIT Bombay, then he was a PhD student at NCRA working on pulsars, and then went off to Jodrell Bank at the University of Manchester for a postdoc, and then came and joined the faculty at NCRA and has played a very important role in the running of the GMRT and work with the GMRT. And currently, he leads the Indian part of pulsar timing arrays and gravitational waves. And this is what he's going to talk about. Over to you, BCJ. Go on.
Okay. Good afternoon, and thanks very much, Shomak, for that introduction. Yes, I seem to be here for a long time, which is fitting with this title of this talk. These gravitational waves I'm going to talk are there for a long time, 15 to 20 years before you detect them. So good afternoon to everybody. These are really exciting times. The ink on the first direct discovery of gravitational wave is not even dry, and we already have very interesting discoveries. The second binary neutron star coalescence event and really massive 148 solar mass event in the O3 run of LIGO. In addition to the 11 events discovered in the O1 and O2 run, including the first binary neutron star merger. So the gravitational waves are here to stay, which is very nice and is very encouraging for us also. So in this talk, I will try to convince you that we, the pulsar astronomers, are taking our final baby steps towards finally detecting the very low or ultra low frequency gravitational waves, which are complementary to the gravitational waves which LIGO detects. And I'm presenting this talk on behalf of collaboration of brilliant and excellent hardworking students and my brilliant colleagues in the Indian Pulsar Timing Array Consortium. Basically, this is all the fun which I have with all of them, and they all have produced wonderful results. I would also like to dedicate this talk to my mentor, Professor Govind Saroop, who was an eminent institution and instrument builder. And it was he who initiated me and got me excited about this topic almost 30 years back by his comment, by his very jovial comment of pulsars bobbing in the space-time carpet. So he passed away in the beginning of this month. So this talk is dedicated to him. And I also thank the organizers here for giving me this opportunity to provide an account of what we are doing with the instrument which he built, which is the Giant Meter Wave Radio Telescope. So with that introduction, let me start. Okay. So I'll first give a historical introduction to gravitational waves and then move on to the sources for low frequency gravitational wave, and then describe the theory and practice of the instrument which I am going to talk about, the pulsar timing array. This will be followed by the results and a description of pulsar timing array built using this excellent instrument in our own backyard, the upgraded giant meter wave radio telescope. And finally, I will talk about the current status of the quest for these gravitational waves by pulsar timing array, and some of the very, very recent results which have come in just last 3 to 4 months. I'll conclude with the future of this particular field. Okay, so let's look at the history of gravitational waves. It's a very, very long path. Okay. I think the gravitational waves, in some sense, started with Newton, because gravitation started with Newton. But it was James Clerk Maxwell's field theory about electromagnetism, in which, while sort of postulating that theory, he also explicitly stated that there could be gravitational wave radiation. And this idea was taken by a brilliant electrical engineer and physicist, Oliver Heaviside, in 1893, where he tried to develop the gravitational wave radiation. While Einstein was busy postulating the special theory of relativity in 1905, Henry Poincare was already showing that you can have retarded potentials, giving you a quadrupolar signature of gravitational waves. And something similar was done by Abraham while Einstein was trying to formulate the general theory of relativity, although he got some of the elements of gravitational wave wrong there. And Einstein eventually went on to propose the general theory of relativity in 1916, but he didn't believe in gravitational waves in 1916. In fact, his initial reaction was that such waves may not exist. And part of the reason was the mistakes in the coordinate systems which he did for calculations of the waves. And eventually he rectified this and published a paper in 1980, only to retract it 20 years later in 1936. And really speaking, it's only 20 years post 1936 that Pirani and others sort of established the theoretical existence of gravitational waves. But from this conjecture, it took another 60 years before the gravitational waves were indirectly detected. And that was in the first double neutron star or pulsar system, pulsar B 1913 plus 16, where Hulse and Joseph Taylor showed that the orbital loss of energy of this binary system is exactly accounted by the implied gravitational radiations. This is what is shown in the plot on the right-hand side, where over 40 years, the prediction from general theory of relativity agrees excellently with the observations. And this has now been shown in many other double neutron star systems. But this was an indirect detection. And to many in this audience, I did not sort of show this plot also, which is about 5 years old now. The first direct detection by the advanced LIGO of this binary black hole coalescence finally established that gravitational waves are there. So, analogous to the electromagnetic spectrum, the gravitational waves also have a spectrum. And what LIGO discovered was in the higher frequency band, which is in hertz to kilohertz, and that's where the terrestrial detectors are sensitive. What I am going to talk about today is in the ultra low frequency regime of the gravitational wave, which is this orange window here, which extends from few microhertz to few nanohertz of frequency. And this is where the pulsar timing arrays sort of sit. And as you can see, they are very much complementary, just in the way radio astronomy is complementary to optical or to high energy astronomy in the electromagnetic domain. The pulsar timing arrays are very complementary to space-based interferometers like the proposed ELISA or the terrestrial detectors like advanced LIGO. And they give you a totally different picture of the universe because they are sensitive to different types of sources. So what are pulsar timing arrays? Pulsar timing array is essentially a celestial detector of gravitational waves, which uses an ensemble of very widely separated pulsars in the sky, or widely distributed pulsars in the sky, with the primary aim to detect gravitational waves in the vicinity of the Earth. Now, the frequency of the gravitational waves which we are talking about is so low that to detect these frequencies, you need to make observations over decades. And these decade-long campaigns are very demanding campaigns. And they demand patience not only from the observers, but also from the time allocation committees which allocate time for the instruments like this. And many times that patience is not there. But the nature of this experiment itself is a very long-term sort of campaign. Typically, the period of these gravitational waves is of the order of 10 years, which is about 10 to the power 8 seconds. And that is how the frequency which we are detecting is of the order of sub-microHz or nanohertz. And the wavelength is of the order of a few parsecs and so on. Since the periods are of the order of year or decades, the sources which would produce this would have orbital periods of that order. And such sources can only be supermassive black hole binary systems. And a good prototype of such a source is the source OJ287, which is a blazar or a BL-lac object at a redshift of 0.3, which is believed to be found from mergers of two galaxies, and the two black holes have become a bound system, with one black hole having a 150 billion solar mass, and the other one very heavy and compact, 18 sort of billion solar masses and so on. It's also an eccentric source, and as I'll show later on, and this excellent animation which you see has been made by one of our young members, Abhimanyu Sushobhan, who has been working on this along with another member, Lankeshwar Day, and I'll have more to talk about this later on. But this is the kind of typical prototypical source which would produce the gravitational wave. However, such sources, the gravitational waves from such sources are very weak and unlikely to be detected. So what the pulsar timing array tries to detect is not from one such source, but from an ensemble of these sources. Now, the hierarchical assembly scenarios of the evolution of the universe suggest that there have been several mergers of the galaxy in the history of the universe. And all of these would form a large number of supermassive black hole binary systems like the OJ, which I showed earlier. So a random superposition of the gravitational waves from each of these supermassive black hole binary systems forms a background, which is known as stochastic gravitational wave background. And this depends on the range of orbital period, the history of the merger or the galaxy evolution, eccentricity, and several other factors. So based on an assumption of circular binaries and certain assumptions from the astrophysics, you could actually derive a spectrum for this stochastic gravitational wave background. And that spectrum is given here, where Hc is the characteristic strain of the gravitational, characteristic strain amplitude of the gravitational wave. F is the frequency expressed in ear. So the typical number would be 1 part in 15. And it's a power law. So it has a power law index alpha, which for the simple spectrum which Jaffe and Becker calculated way back in the turn of the century was about two-thirds. Okay. However, this alpha could vary depending on what assumptions you make for background. So supermassive black holes is one way of producing a background. You could have cosmic strings. You could have primordial black holes, which could also produce a background. And they will have different alpha. Alpha is different from this 2/3. But assuming the SGWB formed from supermassive black hole binaries, you should get a 2/3 spectral index. And this is how the spectrum looks like. The dashed line, I hope my cursor is visible, the dashed line which is visible here is the 2/3 Jaffe and Becker spectrum. And as you can see, at very low frequencies, it is high, and then it has a power law slope towards the high frequency, which is not very difficult to understand, because the low frequency gravitational waves will come from supermassive black hole binaries, which are very far apart, which have very large orbital periods. But as they radiate gravitational waves, the orbit will shrink and the frequency will increase. And the evolution of the higher frequency systems would be much faster than the evolution of the lower frequencies. Okay? So you will have a preponderance of supermassive black hole binary systems at the lowest frequencies and less number of such systems at high frequency, and that is how you get a spectrum of the Jaffe-Becker kite. So qualitatively, that is the explanation for this kind of a power law slope. Obviously, the number of such systems will be very small at higher frequencies, and instead of a line, you may be affected by Poissonian errors in those frequency bins. So you will see some kind of a jagged signature, which is what is shown by the other lines. There is much more information in this plot, but I'll come to this at a later point of time. This is just to sort of qualitatively explain why the Jaffe-Becker spectrum looks the way it is. So typically a PTA tries to look for the amplitude of the gravitational wave at the frequency bin of 1 year, which is somewhere here. And that is of the order of 1 part in 15, or few times 1 part in 15. So that is the number which is worth keeping in mind as we go through. Of course, the stochastic gravitational wave background is not the only source. The individual supermassive black hole binaries, if they have a very large chirp mass, they can outshine this background. But these sources have to be really bright in gravitational waves to be well above the background. And one can play the game by putting different kind of scaling relationships and different evolutionary mechanisms of these binary black hole systems to sort of get different types of backgrounds. And that is what is shown in the plot on the left bottom, where the solid lines are all the background and the spectra for different kind of models, for about 12 models or so, which the detailed calculations in the paper, which is listed here. So the simulations by these authors have shown that at least one resolved supermassive black hole binary can be detected if we have a precision of the order of 1 to 50 nanosecond. And again, I would urge you to remember this number 1 to 50 nanosecond, because this is at the crux of the high precision timing which is required in the pulsar timing array experiments. The other interesting source for the gravitational waves at ultra low frequency regime is what is known as gravitational wave memory. This memory is a permanent change in space-time due to a burst. The burst could be because of hyperbolic passage of a compact object near another object, something like the gravitational bremsstrahlung, like the electromagnetic bremsstrahlung, which could be a small burst. And this kind of a burst is called as linear memory. And this was all worked out by Fausta in 2010, from where these two plots have been taken. The left-hand side plot is for this kind of a hyperbolic passage, which is of course non-oscillatory. And the gravitational waveform can be computed from the second derivative of the quadrupolar moment, the I22, which is listed in this figure. And one can see it has a real and imaginary part, and the imaginary part has a DC value post the event. The event is happening at t equals to 0. So post the event, there is a permanent deformation which is left in the space-time, and that is what is gravitational wave memory. The same thing can also happen in case of supermassive black hole binary coalescences. Okay, so the coalescence will happen at a frequency which is much higher than the PTA frequency range, but the effect of the coalescence would be a burst, and that burst would leave a memory which is detectable by PTA. And as of now, because PTA is composed of freely falling masses, PTA or in future LISA are the only two instruments which are likely to detect a gravitational wave burst with a memory. It's much harder to do that with terrestrial detectors like LIGO. So this is another interesting source for gravitational waves. So all these sources produce low frequency waves, and a pulsar timing array tries to measure these low frequencies. So I will now move on to explain how the pulsar timing array detects these changes in the space-time because of a passing gravitational. It does so by using excellent clocks known as radio pulsars, a schematic diagram of which is shown here on the left top. Radio pulsars are highly magnetized rotating neutron stars, and they are very massive and they are very compact. About 1.4 times solar mass is their mass, and about 10 kilometers diameter. This means they have a very large moment of inertia, and that leads to an extremely stable period or clock-like mechanism. The stability of the period is 1 part in 100 quintillion. Quintillion is 10 to the power 18. Okay, so they are like exceptional clocks, and this clock-like nature plays an important role in their usefulness for detection of gravitational waves. This was realized way back in 1978 by Sazin, who undisputable was the first person to propose using pulsars for detecting gravitational waves in the early era. And these are the four gentlemen who sort of developed the whole paraphernalia of pulsar timing array. That Euler, soon after Sazin, sort of proposed how we can use pulsars to measure the closure density of the universe. And then based on his ideas, Backer, along with Hellings and Down and Foster, developed much of the theories of using pulsars and the modern concept of the pulsar timing array. In fact, he coined the term pulsar timing array. And he was one of the most dedicated astronomers who worked for almost 15 years to detect these waves just before his death. Okay. And his legacy is being continued by the Americans in the nanograph. The other person who has been doggedly pursuing these waves is Dick Manchester in Australia, and I'll have something to say about the instrument which he has built in Australia. So these were the four gentlemen who historically sort of proposed the concept of PTAs, and that is what we are trying to sort of implement nowadays. The principle of the PTA. So essentially the gravitational wave signature near the Earth leads to a tiny change in the space-time metric. And this change leads to a retardation or advance in the travel time of electromagnetic radiation. And since the pulsars are sources in which the radio beam is anchored on a rotating star, essentially it pulses with the periodicity of the rotation of the star. This advancement and retardation can be measured in terms of comparing the actual arrival of a pulse with a prediction of a simple rotational model of the neutron star. So the difference between these two quantities gives you the difference in the spin frequency of the pulsar, and a fractional change of the spin frequency is related to the amplitude of the change in the space-time matrix by this particular expression here, where h is the characteristic amplitude. The term in the blue is in the vicinity of the star. Okay, so if you look at this figure, which is denoting the coordinate system and the relevant angles, the gravitational wave is propagated. The Earth is at the origin of this particular XYZ coordinate system, and the gravitational wave is propagating in the Z direction with its one of its polarization making an angle psi with the x-axis. The pulsar is in the XZ plane making an angle theta. So given this geometry, the fractional change can be written by this expression, where HT is the strain deformation near the Earth, and that is called as reception or the Earth term, which is denoted in blue in this expression. The strain denoted in red is actually the retarded strain which is happening near the pulsar, and hence it's called as emission or the pulsar term. So to be able to measure this fractional change in the frequency, you need to be able to measure the frequency of the pulsar. And this is done by using a pulsar astronomy technique known as pulsar timing. I don't have much time to go into the details of this technique, but essentially what pulsar timing does is it compares the prediction of pulse time of arrival from a rotational model of star with that of the observed time of arrival. at your observatory, keeping track of all the rotation cycles of the pulsar. And as you do this again and again over 1 year, 4 year, 5 year, 10 year, and 15 year, your precision keeps improving because you're given your phase value, the T increases and your precision in delta mu keeps increasing. And that's the key concept in the improvement of the precision of time. Of course, the actual recipe is much more complicated because it involves a model to predict the time of arrival. And that model involves terms about solar system. It involves terms about the pulsar rotation itself and the interstellar medium and various other relativistic and non-relativistic effects. But essentially, if you start at a particular time, you can make a prediction at time t0. You can make a prediction of the time of arrival of a pulse at t1. And then you can calculate, assuming the rotational model, how many number of pulses have gone by. This number n will have an integral part, which is the number of pulses which have gone by, and a fractional part, which should be 0 actually, but it may not be 0, and that is how you sort of improve your modeling. And this fractional part is called as timing residual. So you minimize this timing residual in a least square sense, counting each pulses accurately, and that is what refines your model of the system, which includes a large number of parameters. Again, I will not go into the details of what these parameters are. So they are about the spin parameters, the Keplerian parameters, the post-Keplerian relativistic parameters, and so on, and the parameters about the interstellar medium. But essentially, if your model is good, you will get a residual which is white noise-like. Okay? So it will have no systematics. On the other hand, if there is systematics, then there are unmodeled parameters. And one of the unmodeled parameter would be the gravitational wave. So one could appreciate from here that the gravitational wave is actually hiding in those residuals. And the better is your model, the better is your chance of getting the gravitational wave out. And this is not an easy task, as I will explain a little later. Now, in principle, apart from the gravitational wave, there are other reasons why you can have systematics. You can have timing noise, you can have the interstellar medium playing foul. So a single pulsar is not a good idea to find out gravitational wave because it could be affected by things other than gravitational waves. However, if you are interested only in the Earth term, the residuals from all pulsars will be affected in a certain well-defined fashion by the passing gravitational wave. And hence, the systematic in all the pulsars would be correlated. And this was the principle proposed by Hellings and Downs in 1990, where they said that if there are two pulsars with an angle zeta between them, you should see a correlation which is of the form given by this particular expression, and which looks schematically in this particular way, where the x-axis is the angular separation and degree, and y-axis is the correlation. Okay. If you may, this ensemble of the pulsars is called as PTA, and if you may, this pattern is the antenna pattern of the PTA. Since the stochastic gravitational wave background excites this full antenna pattern, if there is a stochastic gravitational wave background present, we should see the signature very, very clearly. So that is the sort of basic principle behind the pulsar timing array. However, this is easier said than done. This requires very high precision measurements, which requires tuning your instrument, the radio telescope, to a very high degree of precision. And it's a painstaking and lengthy process, which can easily eat up first 4 to 5 or 6 years of your experiment, which is what has happened with most PTAs. You need, what kind of precision you need? You need about nanosecond pulsar timing, and qualitatively it's very easy to understand why nanosecond. Okay. As I said, the Jaffe and Becker spectrum, we are interested in measuring a 1 part in 15 measurement. And for comparison, in LIGO, this measurement was 1 part in 22. But unlike LIGO, which was 4 kilometer arm, here the arm length of our detector is about a parsec. Okay. So by implying a simple light travel time argument, you can find out that a 1 part in 15 measurement on this arm length of 1 parsec is about 10 nanosecond in light travel time. Okay. So we need a precision of about tens to hundreds of nanosecond for doing this. And that is where the all the hard work of PTA lies. So the aim is to detect helix and down curve, which is the spatial correlation, and an amplitude of about 1 part in 15 and a spectral index of about 2/3, as I showed earlier. And this requires an ensemble of pulsars. So what are the prerequisites for forming a good PTA? So a good PTA should have clocks where you can measure this delta nu to a great accuracy, which means they should be very stable clocks. You should have, to get the spatial distribution, these clocks should be distributed uniformly across the sky. And to be able to measure their time of arrivals accurately, they should be bright pulsars. And their light curve should be stable. And what is of importance to UGMRT and in PTA, the interstellar medium should not play spoil sport, or if it does play spoil sport, as it does, as I'll show later on, you should have a way of characterizing that. So these are the basic requirements for a good PTA. So you need good clocks. As of today, about 3,000 pulsars have been discovered in our galaxy and in our satellite galaxies, but not all of these pulsars are useful. And that can be seen from this diagram on the left, where on the x-axis you have the spin period, and on the y-axis you have the spin down, or the derivative of the period. So if you plot all 3,000 pulsars on this diagram, there are three distinct clusters. The clusters on the top hand side have very large p dots, and their periods are not very stable. On the other hand, the cluster on the left bottom side of the plot, these red points here, have periods of the order of millisecond and a typical magnetic field which is very low, 10 to the power 18 or 17 Gauss, which means that the spin down or the change in their period is very, very low. So these millisecond, so-called millisecond pulsars with 10 to the power 19 kind of P dot and 10 to the power 9 Gauss magnetic field are the excellent clocks which are generally used for gravitational wave detections. There are a few exceptions, but many of them can be used. We have about 300 of them, but not all 300 are useful. So as of today, about 75 only are used for PTAs. And even these suffer from various type of noise sources. Now, I told you that the gravitational wave period is very long. It is years. Okay. So the changes which you will see in the residuals will be over several years. And such kind of a process is known as a red noise process. Unfortunately, the rotation of the millisecond pulsars itself sometimes varies slowly. It wanders. And in addition to that, what we have found out in the last 5 years is that we don't know our solar system very well. So the barycenter of the solar system itself can oscillate by about 100 meters. And this can introduce another source of annual noise. And last but not the least, the dispersion in the interstellar medium and the scattering by electron inhomogeneities in the interstellar medium can itself change very slowly over periods of a year. And this slow change can introduce another red noise. So all these sources of red noise are covariant with the gravitational wave signal. And currently, this is the biggest challenge to separate the gravitational wave signal from these other types of noise. So, despite these challenges, PTA experiments are maturing. And we have 3 mature experiments. The Parkes Pulsar Timing Array experiment, which uses about 1,600 hours or about 40 days, about 3 months in a year, only observing pulsars for gravitational waves. Then the American experiment, which is the nanohertz gravitational wave observatory, or nanograv, which uses about 800 to 1,000 hours of green bank telescope time and the Arecibo time. Okay. So about 45 to 50 days of in a year to do this kind of an experiment. And the latest is the European Pulsar Timing Array, which uses all the European telescopes. Okay. All these PTAs share their data and collaborate in what is known as International Pulsar Timing Array, or the IPT. In addition to these established and matured experiments, there are new emerging PTAs coming out. And one of them is the one which I'm going to talk about today, which is the Indian Pulsar Timing Array, which I may just point out uses a very small fraction of the time which the established PTAs use. You know, we typically use only 180 hours of GMRT time in a year compared to 2000 or 1000 hours for the other experiments. So we are limited in our time usage, but still we are slowly sort of coming online. There are future ones like South African and Chinese PTAs which are also proposed. So the Indian Pulsar Timing Array experiment in PTA uses the upgraded Giant Meter Wave Radio Telescope and the UT Radio Telescope, the two facilities of Tata Institute of Fundamental Research. And it is a collaboration of 24 research scientists, including 10 students and 6 PDS from 16 institutions, and is a member of International Pulsar Timing Array. The unique contribution which in PTA makes are the twin advantages of UGMRT, which is a very wide sky coverage and a low frequency coverage. And both of these are important for the kind of contributions we make to IPTA. GMRT has been recently upgraded with wideband feeds, and InPTA uses the multi-band, multi-subarray, and multi-beam nature of UGMRT for timing these pulsars. And in addition, some of us, Yashwant and myself, have spent a lot of time in improving the instrument, in getting stable hydrogen measure and other things to work so that we can do high precision timing comparable to the other PTA experiments in the world. But despite all this, the main advantage of GMRT is its 300 to 1400 megahertz seamless low frequency coverage. This is a coverage which no other PTA experiment enjoys, and that is why GMRT becomes unique. And because of this coverage, the two main contributions of InPTA are the precision DM estimates and the characterization of interstellar medium systematics in PTA data. And I'll show some results on both of these in a short while. Before I proceed, I would like to share this Rogues gallery with all of you. Any large effort like this, large experiment like this is driven by motivated, hardworking, and brilliant students. And the first row shows the students involved in our project, out of which two of them, Lankeshwar and Avimanyu, TIFR students, are already very active in the IPTA collaboration, making major contributions there. And these two, along with Dhruv, who is going to give you colloquium next Thursday in IUCAA, these three members are also on the job market. So I would just sort of advertise that they are there up next year on the job market. And these are ably supported by our postdocs and my nice colleagues who work really very hard and at the same time make it fun to work with all of these people in this particular exciting instrument. Okay. And I would just point out that on the top we have this logo, which is the InPTA logo. Okay, so what is our contribution? To understand the contribution of InPTA to IPTA, I would very briefly mention what ISM does for precision timing. So ISM actually introduces two important effects which have a effect on the precision of the TOAs which we measure. One of them is the dispersion in the interstellar medium, and what is shown here is the pulse of this millisecond pulsar 1909-3744 as a function of frequency. So on the x-axis you have pulse phase, on the y-axis you have the frequency. And you can see that the pulse arrives at progressively later times as you go down in frequency. So this dispersive effect is one of the issues. The other issue is what is known as pulse scatter broadening, okay, which is also a strong function of frequency. So what is shown in the left plot is a template of the pulse at high frequency. As you go down in the frequency, the width of the pulse increases. It actually develops an exponential tail. And this is because of the scattering of the pulse by the inhomogeneities in the interstellar medium that we see this kind of a broadening. And both these are important systematics for the PTA. They are important because a variation of about fourth decimal place in the dispersion measure causes a shift in TOA by about 200 nanoseconds. And as you had seen earlier, that this is of the order of the gravitational wave amplitude which we are trying to look for. So we need to account for these variations very accurately. Not only that, epoch to epoch variation of pulse scatter broadening causes a profile change and evolution with frequency, and again a systematic shift in TOA. The combination of these two causes a bias in the dispersion measure estimation, and this is a new result coming from UGMRT. And both these effects are very strong functions of frequency, nu to the power minus 3 and nu to the power minus 4.4, which means that 300 to 1000 megahertz is the best suited frequency range to characterize these systematics. And as I said, the advantage of GMRT is this precisely this frequency range. So UGMRT is uniquely poised to provide this frequency range and this kind of a data which other PTS don't have. So in addition, we have wideband systems in the upgraded GMRT. So this is about 200 megahertz at 1450, and this wideband system allows us to do in-band dispersion measure calculations, which give us fairly high precision, as I will show you. Also, the in-band evolution of the pulse scatter broadening allows you to characterize the pulse scatter broadening fairly accurately. Usually, so the plot on the right-hand side, the x-axis is log frequency and the y-axis is the broadening time scale, tau, in milliseconds, which is of the order of 1 millisecond at low frequency. Okay. And I would emphasize that you should note that because these pulsars themselves have a period of 2 to 6 milliseconds. So we are measuring a very small, tiny fraction of that as scatter broadening. So this scatter broadening can be evolves as a strong function, and its evolution with frequency can be measured by fitting the scatter broadening at different frequency within the band. So the band here is 300 to 500 megahertz, and you can fit these things together. And the slope of this power law is giving you the typical spectrum of the turbulence in the interstellar medium. Okay. So you can characterize this by observations very easily with the GMRT in the in-band observations. So when you do that and use these measurements to find out the dispersion measure of the pulsar, you can actually achieve very high degree of precision. And not only we use the in-band measurement at band 3, 300 to 500 megahertz at UGMRT, we also combine these in-band measurements of time of arrival with the high frequency band, which is band 5, 1260 to 1460. And this simultaneous combination over a full decade of frequency allows for very high precision measurements of dispersion measure. What is shown here in this plot is the comparison of our measurements, which is the red point and the black points on the right-hand bottom corner of this plot. X-axis is NJD and Y is the dispersion measure. And the blue points denote the measurements by the Nanograph PTA over there recently, just 1 month back, they have released some data, 12.5 years data. So we have just compared our measurements with their measurements, and you can see that our measurements are fairly consistent with them. But what you can also see is that if you use only in-band and simultaneous combination of multi-band observations, there seems to be an offset. And this offset is something which is very new, which we have hit upon in the UGMRT observation, and I'll briefly refer to it later on. So we have been doing this for a sample of pulsars, and we are routinely hitting 4th decimal place measurement of the DM. So we can correct the high frequency TOAs of other established PTAs of the order of 100 to 200 nanosecond. And in some pulsars, we can even go down to the 5th decimal place, which means that we can remove about 21 nanosecond jitter from the high frequency TOA for the other PTA pulsars using the GMRT measurements. This 5th decimal place measurement with GMRT is one of the best in amongst all of the PTAs. But even more important is what the scatter broadening does to the DM measurement. Shown here in this plot is GMRT measurements from in-band measurement of that spectral index, which was the slope which I showed earlier. So this slope of this line is called alpha, and that frequency scaling index is what is plotted here. It should be for a Kolmogorov turbulence, it should be of the order of -4.4. What we see for this pulsar, millisecond pulsar 1643 minus 1224, it's of the order of -2 or so, which itself is an interesting thing to sort of interpret. But more importantly, from the PTA point of view, it is not constant. It keeps changing. Okay? So all the way from -4 to almost -1.5 and so on. So there is an epoch to epoch variation of scatter broadening. And what this epoch to epoch variation of scatter broadening does is that if you measure the in-band versus multi-band DMs, you find that there is an offset, which is what was there in the earlier plot which I showed here. So you see a difference in these two measurements, and that difference is actually coming. This is for the same pulsar. This difference is actually coming basically because of this epoch to epoch variation of scatter. So we have in the last few months developed a method to deconvolve the scatter broadening and do a precision timing without scatter broadening. And what we find is that if we do that, we find that the scatter broadening is actually introducing a bias in the multiband DMs, especially if the DM at the low frequency is measured with a very narrow band observation of about 20 to 40 megahertz. It so happens that all the other PTAs use narrow band observations of about 20 to 40 megahertz, unlike our 200 megahertz one. So it is quite possible that the dispersion measures measured by them have a bias. Now, this is something which we are trying to confirm right now. So it is a preliminary result and work in progress. So I would say that take it with a pinch of salt. But we have done this analysis on 1939 plus 2134, 1643, 1713, and so on. And we see similar signature on all of these pulsars. So we feel reasonably confident that for the first time, we have discovered a bias in this. And this bias is not something new. It was theoretically predicted by Cordes et al. 2 to 3 years back. But they sort of couched it in a terminology which said frequency-dependent dispersion measure. So I don't think we have frequency-dependent dispersion measure, but we have a bias. And that bias is coming because of multipath propagation in the interstellar medium. And I think this would be a good proof of that for this thing. And this is some work in progress, which we hope to finish very, very soon. Now, what this bias does is that it will introduce a red noise systematic in anything which the PTA datasets discover. And I think this is an important thing to account for before we claim a detection in the gravitational waves. We also do other things, and one of the things is mode changing. I don't have time to go into in this detail, but basically mode changing is a change in profile of the pulsar from epoch to epoch. And this change in profile from epoch to epoch also introduces a systematic change. And in this pulsar 2124, we find a mode change for the first time, and another publication is in preparation for it. In addition to the data which I mentioned, our students are doing scintillating work in other theoretical campaigns. And one example of this is the work by Lankeshwar De, Abhimanyu Shobhan, and Gopakumar, who are our collaborators, on this source OJ287, which, if you recollect, I said is the prototype of the supermassive black hole binary system. This is believed to be a supermassive black hole binary system because over the last 120 years, it has shown electromagnetic flashes and quasi-periodicity in the electromagnetic flashes. And Maury Waltonen and others have doggedly followed this source over 30 years to establish that it has a periodicity. And the recent work done by Lankeshwar has confirmed that you can actually predict these flashes to about 2-day accuracy and so on. And this beautiful animation by Abhimanyu shows you how the flashes occur, and they actually sort of fit perfectly well with this curve on the bottom left-hand side. Also, a lot of gravitational physics has gone into this because the orbit of the less massive black hole precesses, and that precession can also lead to a jet precession of this blazar or the BL-LAC. And the future upcoming campaigns, especially VLBI campaigns, would try to sort of measure this. And again, some work on this has been recently published by Yeshwar, Gopakumar, and others. Of course, such sources as individual sources will give you a PTA timing residual. But what is a bit disappointing is that the timing residuals are of the order of 1 to 2 nanoseconds, which is way below the precision of the PTAs which we have today. But it gives these calculations have sort of trained our collaboration members to do the same thing for more massive chirp masses binaries, and also get involved in the searches for eccentric sources. This OJ287 is a highly eccentric source. And because of eccentric sources, what you have is you have some kind of a frequency modulated spectrum, FM spectrum kind of a thing, where you don't only have a fundamental of the frequency in gravitational waves, you have higher harmonics also. And Gopakumar and his students are working with the nanograph collaboration to try and constrain or put limits on such individual supermassive black hole binary systems, which could be eccentric. Okay? And that's an important piece of work which is going on. There was just a IPTA meeting yesterday, which finished, okay, last 3 days. And this work was also mentioned in that, in the IPTA meeting. So I just wanted to highlight that many of our members are not only contributing in NPTA, they are also contributing in IPTA working groups. Okay, so the last 6 to 7 minutes of my talk, I would, do I have time, about 5 to 10 minutes?
Yes, of course, yes. Go ahead.
So the last 5 minutes, I would like to update you on the current status of the International Pulsar Timing Array. So I talked mostly till now about our own experiment and the results from our own experiments. But let me now bring you up to date on what the IPTA has to say. And this is really up to date and really breaking news, because from Monday onwards, there was a virtual International Pulsar Timing Array meeting, which was quite painful because it was in 3 time zones. So last night, for example, I was awake up to 5 o'clock listening to the final session. But the results are really exciting. Okay, so all that late night waking up was really fun and was very exciting. So this is a little older plot, which I showed earlier also from Burkes Polar in 2019, which shows all the limits. So I already mentioned that this dashed line is the simple Jaffe and Becker spectrum. The gray circle, the gray triangle, and the gray square are the 1 year limits, upper limits from the Parkes Pulsar Timing Array. The circle is PPTA. The triangle is nanograph, and the square is the European Pulsar Timing Array. So these are the 3 limits from these things. And the dotted line is actually the nanograph sensitivity curve. So you can see that the PPTA gives you probably the best limit, which is of the order of 2 times 10 to the power minus 15. And it's actually sitting on Jaffe-Becker spectrum. So one question which naturally arises and arose in our mind was why we are not detecting the gravitational wave background. Okay. We should have detected the gravitational wave background already, and not today. P15 is 2015, so 5 years back, maybe before the LIGO also. So the fact that we are not detecting gravitational wave background could be because of several reasons. One could be that there are unmodeled systematics in our TOAs, which we don't understand, and we need to work on that. And that is one angle on which a majority of the IPTA collaboration is working on. The other is that the physics itself is at fault, or the astrophysics itself is fault. So the Jaffe and Becker assumes many things. It assumes that the binaries are circular. They need not be circular. They could be eccentric. And if you are eccentric, then the eccentricity gives you a band, which is this kind of a green band. And you see that the spectrum actually goes down. The eccentricity, what it does is it pushes the power in a frequency bin to higher frequency bins because of the harmonics, which I said earlier. So obviously at lower frequency, the spectrum comes down, higher frequency, it goes up, but overall it goes down. So eccentricity is one of the things which was not there in the Jaffe-Becker thing. People have tried to do that. But in addition, the scaling relations which were sort of used to get the chirp masses, the evolution of the supermassive black hole binary itself may not have been the right astrophysics. So if you change those models, then your estimates can change in the spectrum. And that may be one of the reasons why this is not happening. Another fundamental assumption in all these calculations by William and Cesana and others was that the late inspiral of the supermassive black hole binary system happens purely under gravitational wave radiation. That is, the binary orbit is shrinking just because of the loss of the gravitational wave energy. Now, that may not be true, because this is happening in a galaxy which is full of gas and star. And the dynamical friction of these things can actually stall the evolution of the supermassive black hole binary. And especially near the last parsec, the two may just stay put. And that's known as the last parsec kind of a problem there. So if you have this kind of a stalling, then you may actually not be able to, you will have a spectrum which will have a very different shape than the spectrum which I showed earlier. And there have been some work by Dworkin and others to sort of explain the non-detection on the basis of that. So that is probably one of the reasons why we have not detected. But in addition to that, the other problem which one could have is that we are not sensitive enough itself. We ourselves are affected by various kinds of systematics. Okay? And that is both good and bad. The bad news is that it affects our ability to detect these tiny gravitational waves. But the good news is it produces some other astrophysics which was not constrained earlier. And some other astrophysics right close to our own home, the Earth. Okay. So Earth is in a solar system, and for doing the pulsar timing, we refer all the times of arrival to the solar system barycenter, which is shown schematically in this particular diagram on the right-hand side. And that is done by actually calculating the Romer delay, the delay of light travel time delay from the solar system barycenter to the observatory. And that is just a dot product of the vector S, which is pointing towards the pulsar, and the vector RSSB, which is pointing towards the Earth. And in this, the RSSB depends on the dynamical masses of the planets, planet-moon systems, and asteroids. So to be able to get the precision which we want in the solar system, you need to be able to define the SSB to a very great degree of precision. Unfortunately, even NASA does not require that kind of a precision. And in 2015-16, it became clear to us that there could be hundreds of meter uncertainty in the definition of the solar system barycenter. And that could actually give us all kinds of systematics in our data sets. So this is called as solar system ephemeris problem. And people have actually used to use these uncertainties to constrain things like masses of dwarf planets, masses of asteroids, mass of Jovian systems, and also to look for unidentified massive objects behind the sun, which you can't see with a telescope. Okay, and these are some of the constraints. An interesting paper to read is by Caballero et al. 2 years back on this aspect. But this has also led to development of all kinds of ephemeris. So here is a long list of the ephemeris from D405 to D441 now. Okay, each ephemeris accounts for various things. In 2011 and 12, when we were just reaching 12 years, the IPTA datasets were very badly affected by Jupiter's orbit and Jupiter's mass, because Jupiter has a similar orbital period. As of today, we are badly affected by Saturn, because Saturn has even larger sort of orbit. And in yesterday's IPTA meeting, Yanjun Guo was talking about even the inner planets. And it's not the masses of the inner planets, but the exact position of the inner planets which could affect the overall Romer delay calculations. And that is what she was sort of talking about. And what is shown here is just sort of a kind of uncertainties which we get for solar system bodies, and which we can constrain from the IPTA kind of measurements. But the bad news, as I said, is that this sort of is sort of taken into our gravitational wave kind of a thing. Last but not the least, and these are my last two slides, we seem to be coming fairly close to detecting the gravitational wave background, despite all these systematics. And this is the hottest result, just submitted 1 month back in arXiv. is the nanographs 12.5-year data released by Alem et al. And the main result there is that they are finding in the nanograph data a time correlation. That is a stochastic process which is common to all pulsars with a characteristic amplitude of about 1.9 into 10 to the power minus 15 at a frequency of 1 year. And the three plots here sort of show evidence for that. I don't have time to go into the details of the plot. Suffices to say that at a gamma of about 4.4, and this is 4.4 and not 2 by 3 because this is done in the spectral domain, in the spectral frequency domain, and an amplitude of 1.9 into 10 to the power minus 15, you have very good posteriors. So this is coming from a Bayesian analysis, which is giving you these kind of posteriors. And they are very confident that this common process is real. And the odds ratio or the base factor of this is of the order of 2.5 sigma detection. But we don't know whether this is gravitational wave or it is some other common noise process. And for that, they have actually done a model comparison, which is listed in this particular table. Okay. And essentially, this model comparison is a model between spatial correlation. So while they see a time correlation, the spatial correlation, which is the Hellingsand down curve, which I told you earlier about, that spatial correlation, there is uncertainty. And really speaking, there is only one sigma kind of a thing. There is some kind of Hellingsand down curve here. As you can see, the nanograph 11 had some hint, but nanograph 12, you do see a sort of a dip here. But it is no significant gravitational wave detection yet. So the preliminary analysis of 15-year data set also sort of confirms this kind of a correlation, but I would not speculate more and say it is early days yet. However, it is quite likely that given these kind of latest results, we are actually fairly close, and the discovery is coming in the next few years. So please keep tuned for future results in the near future. So I'll leave with this concluding remark slide, and I'll stop here. Thank you very much for your attention.
Thanks, Bhal Chandra, for this absolutely sensational talk. Very interesting. I found it very funny that the International Pulsar Timing Array did not get their video conference timing correct. That you had to join a time.
No. Actually, that was not the case. They had three time zones, and so two were okay for me. The third one was not.
Anyway, so just to tell everybody, already people know what to do, but if there are people who are new to this configuration, please use in the participant screen on the right, the blue hands up symbol. There are many already there. So let's go for Shukanto first. Unmute.
Hi, Bhal Chandra. Thank you for a very nice talk. My question is, again, to this very recent possibility for correlated noise. My question is the red noise systematic that you found with UGMRT, which you spoke about some slides ago. Can that have any implications on this possible correlation, or they are independent?
Very good question. I don't have an answer to your question. Even the red noise, the DM bias which I'm talking about is also very new. It's only 4 or 5 months, and we haven't convinced our colleagues. Okay, so yesterday on the sidelines of this Zoom is very good. On Zoom virtual conferences, you can talk all the time when the talk is going on. So yesterday I did have discussions with other people, but I think it will take some effort on our part and some simulation on our part to convince them. And Gopakumar and a new student at TIFR, we plan to actually run some simulations and maybe find an answer to your question. But at the moment, I don't have an answer to your question.
Okay, that's good. Pratik, next. You're unmuted.
Hi, a very nice talk. So I wanted to know, under the Indian PTA, how many pulsars do you observe, and what's the criteria for choosing those? I mean, I know you choose MSPs, but yeah, do they have overlap with the other collaborations?
Yeah, that's a good question. So we started with about 20 pulsars, and these 20 pulsars were chosen in the following way, that they were the brightest of those 75, because obviously we were starting afresh and our timeline is not as large as the other PTAs. So we didn't want to go to the weak pulsars. So we only chose the brightest 20 pulsars. However, our referees were suggested that that is not a good strategy, and they wanted us to limit ourselves to the 6 brightest pulsars, and that is what we have done. There have been discussions between different PTAs in the IPTA forum about coordinating between the PTAs so that we can use, as you saw, that total of about 5,000 to 8,000 hours of time is being used by other PTAs. So if we coordinate, we should be able to do a much better job. But for various reasons, that has never worked out. Okay, and the same has been true for us. So essentially, there has not been much coordination in terms of, to answer your question. But what we have informally done is we have chosen the pulsars where the low frequency characterization would be very useful. For example, this 1909 pulsar is the best timed pulsar in the entire PTA. Every PTA has the best data sets, but it also shows DM variations over a period of time. So having that pulsar in our sample allows us to supply that extra piece of information to the established PTAs. And so that is our plan. And there is a DM data release which is coming up in November and December, where we are precisely going to do that. We will provide all our results to the PTAs so that they can use it for their 15-year data releases.
And how does the ORT help here? I mean,
ORT helps by giving higher cadence. So GMRT is a general purpose instrument, so we can't time these pulsars every week as we would like to do. So we fill up for the cadence by using ORT. But ORT we can't do multi-frequency, so we can only do low frequency observations.
Thank you.
Thanks very much. That's great. Sanjeev next. Unmute. Please unmute your microphone. Go ahead.
Okay, yeah.
Yes, great.
Last 2 months I have been trying to do this, but I can't get the...
the timing, it's all in the timing.
Anyway, very good talk, Bhal Chandra. So I had one question about the statistical methods which you have been using to do this analysis. So about the significance of the event, how would you decide on the significance?
That's a, yeah. You mean the significance of the
detection? How would
detection?
you say that there's a detection and with what significance?
Yeah, that's a great question. And that is a question of great debate within ourselves also. So what constitutes a discovery? See, unlike LIGO, where you had a very nice chirp signal, so and very well defined, well predicted waveform, that's not going to happen for a stochastic gravitational wave background. Okay.
We also have a stochastic background anyway.
Yeah, but you had a much easier thing to do. For us, the problem is, for us, the problem is that we will only creep towards detection. We are not going to one night wake up and say that we have detected it. So this is a matter of great debate in the steering committee and in our working groups and so on. So what we have hit upon right now, it's a empirical definition. It's not something very reasonable, is that if you have the Helling and Down spatial correlation, and you compare it with, say, a monopolar or a dipolar sort of correlation. I didn't talk about that, but basically, if you assume a monopolar signal or a dipolar signal as opposed to the quadrupolar signal, the Helix and Down comes from the quadrupolar signal.
Yeah.
Then you will get a different signal. So you could use these three models and calculate the odds ratio in the Bayesian analysis for that.
Right.
And a base factor of few hundreds would constitute a detection. So that's the operational definition which we are taking right now.
Right.
But of course, it's slightly subjective in the sense that some people say that a lower definition would be better. Some people say no, till you get 1,000, don't call it a detection. So that debate is still there.
Thanks. Okay.
Thanks very much. Thanks, Sanjeev. Pranav Limai next.
Yeah. Hello, sir.
Hi. Go ahead.
Yeah. My question was, we have pulsars like the Vela pulsar, which show quite periodic glitches in their spin periods, and there are papers showing that they can release gravitational waves through their emission. So can we infer something from that?
Yeah, so Vela pulsar is a fast rotating pulsar, and hence its gravitational wave signature, the quadrupolar signature, will come in the LIGO range. The frequency range, PTAs will not be sensitive to detect that, but LIGO will be. And if you hear to the advanced LIGO talks, you will find that there is a continuous wave, gravitational wave group in LIGO, which is actually looking for gravitational waves from mountains on Vela pulsar or Crab pulsar and so on. So there are searches for that. There are limits on that. No detection has been made, but essentially it is it's a LIGO spectrum and not the PTA spectrum. Does that answer your question? Okay. You are muted, Shomak, I think.
Shomak, you muted, yes. And
Sorry.
Bhal, you can reveal yourself. You can be-
Oh, I forgot to.
Go ahead. Sridham, go ahead. You're unmuted. Go ahead, please.
Hi. The discussion I noticed was largely the source of these gravitational waves from these supermassive black hole binaries. There can be inflationary models which can generate secondary gravitational waves at late times, where the peak can arise at the PTA frequencies. Of course, the inflationary gravitational waves will be more isotropic in nature. The question is, are these pulsars distributed isotropically? And is there some way of understanding the direction dependence and therefore understand whether they are from inflation or from supermassive black hole binaries?
Yeah, so you're right that I only focused mostly on the stochastic gravitational wave background because the signal is going to be brightest for that. And you are very correct in pointing out that the inflationary scenarios will also produce primordial black hole kind of a background. The difference between the two backgrounds is in the spectral index of the spectrum. So one way to distinguish the two would be to have a spectrum, and in the latest 12.5-year release, this 1 month old release, they have also tried to fit index-free spectrum and come up with a base factor or a odds ratio for that versus the Jaffe and Baker spectrum. So that is, I think, more than the directionality, it would be the spectrum which would distinguish between the two. On the question of directionality, yes, you are right that if you want to have a really good detection of the isotropic stochastic gravitational wave background, you need to have pulsars which are more or less isotropically distributed in the sky. Unfortunately, that is not the case because the pulsars are galactic objects. So most of the pulsars are in a particular direction and very few in the other direction. So there is a little bit of a problem there, and pulsar searches are trying to rectify this by finding more and more pulsars. So that's one way of looking at that. But the helix and down curve, which I showed you, is the antenna pattern of the detector. So the individual sources, you can actually have some directionality if you choose the right combination of the pulsars. Okay? And some work on this has been done. But again, most of our effort has been on the stochastic gravitational wave background and not on the individual sources, because the stochastic background is something which we are likely to detect first. So both the things which you said are valid and would be needed, and work is being done on that.
Thank you.
Gopu, go ahead next. Gopu Kumar.
Can you hear me?
Yes.
Yes, loud and clear.
Thank you. No. So yesterday we were all listening to, many of us were listening to KJ and his student talking about solar system ephemeris, and they were talking about the inner planets now. Then it's opening a Pandora's box, Balchandra. I
Yeah,
realized that there are co-orbital satellites to Earth with the mass which is not, something like 100 million times smaller than the moon, and that's good enough to destroy many things. So, well, I lost my sleep thanks to that. So, yeah, so I think this is going nowhere.
No. So if you remember the chat discussion on the Zoom chat and also on the Slack, George was posing the same question. Why do we go to solar system pericenter? Can't we find another inertial frame which does not move? Okay.
But it will be dynamical then, yeah.
Yeah, so we need to actually figure out, and somebody suggested galactic center, which I don't think is a very useful thing. But so I think we need to think very carefully about how do we get away from the dynamics. Okay, as long as we are dependent on dynamics, all these Saturn, Jupiter, Mercury, and Venus, which she was talking about, will keep making trouble for us. But the base FM. Gopu, the other thing which if you remember, there was Sion who talked on base FM. That is they average over several ephemeris. So that base FM method is much more robust. And even in this 12.5-year paper, they have shown that with the D431, if I remember, which does not have Saturn mass properly, and base FM, their results are not very, very different. So hopefully we may be able to push the ephemeris under the carpet, but but I agree with you. It's a very messy thing.
Hopefully. Thank you.
Oh, wow. Now you're going to discover minor planets, Elon Musk's car or whatever. Amitesh Singh, come on. Next.
Yeah. Hello. Thank you, sir, for the wonderful talk. I just had a question regarding the NPTA pulsars, the 6 of the brightest pulsars, which you guys are trying to study for these gravitational wave sources. So my question is that after the de-dispersion part, what kind of raw SNRs are we expecting from the upgraded GMRT? And also, you talked about very high SNRs required for the pulsar timing. So what ranges of SNRs does that fall into?
So typically, I would say 200 to 500 SNR is essential to get a reasonably to get TOA uncertainties of the order of a microsecond, which is what is required here. In the legacy system, we were getting typical SNRs of 70 or 60. But with the upgraded GMRT in the first few cycles, cycle 34, 35, we were routinely hitting about 180 to 200. And in the last 2 cycles, we are going up to 400. And so in the brightest pulsar, the 1937 plus 21, the second fastest pulsar, we hit 1000 to 1200 in an hour or so. And so now actually we are, in principle, we don't need that kind of an SNR. But in practice, we still go for that kind of a SNR because we can subdivide the band. So it's a wideband observation. So instead of having a single band TOA, we now subdivide the band into 32 or 64 or 128 channels. And we have one TOA for each of these channels and do what is known as wideband timing, which in the Pune meeting last year, Tim Penucci and others from the Nanograd showed is a far superior technique of timing than anything else. And in yesterday's discussion also, and day before yesterday's discussion in the IPTA meeting, it appears that wideband timing is the way to go. So to maintain the wideband timing, we will still need SNRs between 400 to 1000. So short answer to your question, 400 to 1000.
Stomach muted or what?
Indulekha, go ahead, you're unmuted. Yes.
Yeah, this might be a live question, and I missed the beginning part of your talk also. You were telling that the solar system barycenter, a few meters difference could be there, and it might be creating problems. But suppose you multiple telescopes look at the same pulsar simultaneously, can you sort of, I don't know what word to use, sort of triangulate and fix the keep fixing the barycenter? Can you locate the barycenter like that by matching the pulse profiles by? transformations. They will be slightly different, I expect, for different telescopes, simultaneously looking at the same pulsar.
Yes, it's an interesting idea, and there was a discussion yesterday on this. So essentially what you are saying, Lekha, is that we use a GPS kind of a system. We think that Earth is like a satellite, and we triangulate the satellite's position using the pulsars themselves. That is doable, and I think Gopu and George Hobbs and few others, a couple of students, were toying with the idea to do some simulations on this aspect. I don't know, maybe Gopu can comment on that. But yesterday, while all this discussion was going on in the IPTA meeting, this was also an idea which was being mentioned. So yes, what you say is perfectly possible. How accurately we can do and whether it will solve this problem is a different issue, which one will have to put in more work. But that kind of, we do have to think out of the box like this to be able to improve the sensitivity which we want. So certainly it's possible, but whether we should be, we will, the only thing which will not help is having different telescopes. I think you also mentioned that if you have 3 different telescopes, will that help? No, that will not help, because as far as the distance of the pulsar is concerned, that's not going to be. So the real way to do this would be to have another telescope in, say, some other solar system far away and a third telescope somewhere else. Then you can actually build a GPS, some kind of a stellar GPS, and do this really accurately. But there were some ideas bandied about yesterday in the Slack discussion, and it's worth examining. May work, may not work.
But I thought I heard this in the context of something on the moon. Would the moon help, or you
Yes,
need on the planet? Yeah.
No, moon would certainly help. So if we can build a telescope on moon, it would certainly be useful.
Yash is the last question. Yash has been trying very hard to raise his hand. So here you are. Yash.
Okay, so I have a very naive question. What determines the frequency range which PTA will measure?
No, it's not a naive, it's a good question. Okay, so I said ultra low frequency, microhertz to nanohertz. It is essentially the sources which sort of determine this. I said supermassive black hole systems. So the typical orbital period, say for OJ287, is about 12 years. Okay, so 12 years is of the order of 10 to the power 8 seconds or something of thereabout. Okay, so inverse of that is the frequency. In fact, so that is from the source point of view. You can have a similar argument from the detector point of view, and then that detector point of view is determined by the gravitational wave detection timescales. That is, what is the cadence, what is the minimum period over which you should observe, observe the sources, and what is the maximum timescale over which you will do that. Okay, so again, the maximum timescale comes to about 10 years to 15 years is the detection timescale, and the minimum is about a week. Okay, so those are the two bounds of the. So anything which is less than a week will not fall in the PTA band. Okay, that would be the higher frequency limit of the PTA band, which will generally fall in the LISA band. And things like seconds, which is the LIGO sources, fall in the LIGO band. So the frequency is determined both by the sources as well as by the detectors.
Great, thanks. I see another hand up. Amitesh, go ahead. Another question, and then we'll round off.
Yeah, hi sir. Actually, I wanted to ask considering the statistical errors and modeling errors, what kind of understanding is required for better modeling the pulsar glitches, which are essential for the PTA?
Okay, so this seems to be sort of related to your earlier question. So one thing I should clarify, the pulsars with glitches are not used in PTA because their rotation is not stable. So as I said, if you remember in the beginning part of the talk, for PTA precision to be reached, we need highly stable clocks. And pulsar glitches happen in young pulsars and not old pulsars like the millisecond pulsars. So the young pulsars, the rotation is highly unstable. not only they have glitches, they have random wander of their spin period, which is known as timing noise. So Crab and Vela pulsar are very young pulsars. Crab is just 600-700 years old. It's a historical supernova. Similarly, Vela is also a very young pulsar. So these young pulsars have fairly large rotational instability, so they are not good clocks for PTA. So glitching pulsars are by definition excluded from PTA sample.
Yeah, right. Yeah. Thank you, sir.
Thanks very much. Thank you. And it was a fantastic talk, and the kind of questions it generated, it just shows how successful it was. Thank you again, Bhal Chandra.